So we are going to do Metropolis algorithm. So first step, remove list equals ls to clear the environment, as always. So first, we need to define a target distribution. The target distribution doesn't have to be a proper probability distribution. We saw that. So I think we used uppercase P. We had 4 states, or was it 5? I think we had 5 states, right? From last time, it was 3, 5, 8, 4 states. 1, 2, 2.
Is that what last time was?
I don't think so.
No.
There was an 8 somewhere.
There was
8.
8, and then it was like, not 2, 4. Oh my god.
So that is the target distribution, and we can plot our theta is simply 1 to 5 because we are looking at discrete theta values. So I'll call theta to be simply 1 all the way up to 5. 5 different states. Probability, plot theta, comma P, LWD equals 2, column equals totals. Target distribution doesn't have to be a probability distribution. X log expression 2, Y log expression P of 2. Should work. If it doesn't, we'll figure this out. I'm going to define type equals L of H. So looks kind of nice. So there. So that is our population distribution, or target distribution. So that's what we're trying to get to. So how does the algorithm work? First, we've got to know the number of iterations we are going to go through. Yes. So we'll define the number of steps that we plan to take. Number of iterations. I'll call 1,000, keep it simple for now. And the very first step is to propose a state. So for I in 1 to n, I want to propose a state, and the proposal state I am going to uniformly choose from 1 to 5. So sample 1 to 5. 1 successful. So theta underscore dot proposed. I'll call it P. So proposed theta. Now I want to keep track of the thetas that we simulate. So I have to initialize first. So theta of p is 0. I'll put that as, I used I. So theta dot p of I is going to use the first proposed theta. I need a current theta value. So pick a state. Which one do we want to go to start? Yeah, two. That's exactly where I wanted to go. State 2. So the current state is 2. Now, what is the next step?
To check the probability of which state we're going to next.
The probability of doing what?
Yeah, shouldn't we generate a random number between 0 and 1?
That's after, but before that step.
The probability of going up 1, staying, or going down 1.
So we want to find the move probability.
Right.
Yes. So if, well, let me call it P dot move. It is a probability of a move, which is 0.5 times the minimum of our theta p value or p values. So uppercase P, proposed theta, so theta dot p of I over uppercase P, the current value of I, and what is the next argument? 1. If P dot move is equal to 1, what should I do?
You should move.
I should move. So theta dot. So if the probability of move is 1, the next state of theta that I would take is the proposed value of theta. Yes. Else, if should we do else or should we do else if? Why else if?
Because there's 3.
There are 3 options. The other one is stay. So if P move we made a slight mistake. Can we recognize what that mistake is? It is in the if statement.
It should be 0.5.
0.5,
Yeah.
yes. Divided by P theta dot C of I. If it happens to be that, what did we do? Or what should we do? I called it U, the random number. So running. And I would only move if whatever value that I generated is less than P nu. First condition, P mu equals 0.5. Theta dot C, the next state, I'm accepting the proposed value. And if that is not the case, I generate a uniform. And if U is less than the uniform that I generated, I move to the proposed value. Otherwise, I reject the proposed value and I stay at the correct position. Yes? Just to recap, what I did is I defined the move probability, which is 0.5 multiplied by minimum of that. If the move ends up being 0.5, which simply means I get 1 there, then I will have the next state to be the proposed state, currently proposed. If that is not the case, then I generate a uniform random variable. Uniform random variable by default is between 0 and 1. So if U is less than P dot move, then I would accept the proposed state and make the move. Otherwise, I will stay where I'm at. So theta dot C of the next state will be the current state. Does that make sense? So that is the random probability that we generate. Now, what we're going to do next is just plot the walk for a few steps. We'll do walk to walk and talk to talk. So plot time steps, we're going from 1 to n. Technically speaking, we would hit n plus 1. So 1 to n plus 1. Theta dot C, the states that we're going to move through, that would be a lot. So maybe I'll just do 1 to 10. The first 10 steps. Type equals both points as well as line. LWT equals 2. ECH equals 19. Color equals red, blue, the walk. The first few steps, of course, we can't retain the first few steps. Remember, I mentioned about the burn-in period, we have to get rid of the first few states. But I'm just doing this to show as to what would happen in the very first few steps. XLab would simply be the step that we take. YLab is the corresponding theta value.
Theta C is
So let's set the seed. Set seed, what would do 2022, so that we get the same result. And the first few steps That's what my walk looks like. So I'm starting at 2, staying at 2, then I went to 3, 3, back to 4, then to 4, 1, then 5, back to 2, uniform distribution. So the histogram of the proposed theta values looks like that. Histogram of the current values are the ones that we accepted. So those look like that. And what's happening?
His aren't normal. Yeah.
So let's say we'll do test of theta dot c. We're going to save it to h. And h dollar counts will be the counts that we have. So the counts happen to be 64, 229, 586, 19, and 103. The actual p that we have, p divided by sum of the normalized probability of 0.111, 0.22, 0.44. That's what I get. So if I divide the counts by the values that we have, which is 100,000, those are the probabilities that I get. It matches up with the second, sort of matching up with the third, but it's not as good. Let's try 10,000, see if it makes a difference. And those are the counts that I get. Still slightly off. Let's try taking this 0.5 away and set it to 1. Slightly better. And p over sum of p. Much better. So that 0.5 is not needed because it's just a probability that we multiply to scale, right? Theoretically speaking. If you get rid of that 0.5 and simply compare the probability of the proposed state to the current state and you run that, I can come up with a histogram for the proposed values.
What did you change? Because mine was over here.
I changed it to 10,000.
I have.
You still get.
Oh, and I got rid of the 0.5.
Yeah, you changed it to 1, it's not.
So minimum, right before minimum, there was a 0.5. I got rid of that 0.5. Yeah. And then change p dot move equals 1. Don't actually need that 0.5 because if we use that 0.5, it is actually going to change our uniform here. So if I use a 0.5 up there, had I used run if 0.5 or run if 1, 0 to 0.5, I would have gotten a better histogram in the previous case. Now, hist theta dot c will have all the current states or the accepted state, this is our target distribution. And I'm going to call Frick equals false so that we get a density. Not that way. So we want a probability actually. So what we can do, so I'm going to save hist to H, called P dot est. That is the estimated target distribution. The counts, each of the bar counts divided by the total n that we have. Perhaps I could put breaks equals 5. Oh, that messes things up. So give it as that. No, get rid of breaks. We don't need it. Read the default value. Oops. So when I do H dollar counts over n, the object H will contain the counts for each of the bars. And if you look at those counts, some of them are 0. I don't want the 0 values. So I'm going to say H dollar counts of those values not 0. So the count values where the count values are not equal to 0. So I got rid of all the 0 values. So when I divide by n, I'm going to get the normalized target distribution. The actual target distribution as a probability distribution would be P over sum of P, the normalized value. So once I normalize the estimated distribution, but P dot est, type equals both LWT2. I'm going to add lines 1 to 5. The actual target distribution. Color equals full, which would be blue. And LWT. Let's see if it did good. It should. And you can see the estimated distribution and the target distribution are a ethnic match or near ethnic match. Yes. And that, in short, is how you code Metropolis algorithm.